Hello! Our team is currently studying at Penn State. The sponsor for our project was Johns Hopkins Applied Physics Laboratory. This paper airplane will be used to convey the hypersonic craft Johns Hopkins is currently working on. Hypersonic means that the craft travels around Mach 5, which is 1 mile per second. The aircraft needs infrared sensors for navigation. These drill bits will resemble those infrared sensors. A glass window currently protects the infrared sensors on the craft. Unfortunately, because of the high speeds, the glass window experiences a lot of heat and eventually fails. Essentially, the team took an entire month to propose potential solutions to this window. After many meetings, we decided on this final design, which was made on SolidWorks software. Materials were then purchased to fabricate this design. In total, it took the team 35 hours to make this design. Right here you can see a Bridgeport milling machine. Because we used stainless steel, fabrication time was much longer than we anticipated, but it was way worth it in the end because we were all happy with the final product. The reason we use stainless steel is because we were eventually going to conduct thermal tests on glass, and we didn't want our prototype to warp in any way during the tests. The following is an assembly of the prototype we used in our Capstone project. Because of constraints such as budget and testing conditions, we were unable to test the original hypersonic conditions. This means we didn't have fancy aerospace alloys or really high-tech sapphire glass for the windows. Instead, 303 stainless steel was used, and for the actual glass windows, our team decided to use soda lime silicate glass. With our team's design, we were able to test the single pane configuration to mimic the current setup on the aircraft, and we were able to test the double pane configuration, which was designed by the team to hopefully increase the survivability of the window. During the testing phase, we also had stainless steel windows, and these were to discover the heat flux of our testing setup. Thermocouples and an infrared thermometer were used to find the heat readings on the setup. A powerful heat gun was used to provide the experiments with sufficient heat, and right here you can see how a single pane setup broke after a few minutes of heating. Every time the team tested a singular pane in the setup, the glass would break after a few minutes of being heated. Here you can see a double pane configuration. Excitingly, every time we tested a double pane configuration, the glass never broke, even after heating the glass for 10 minutes. 200 degrees Celsius was achieved in between the two glass panes, and the top exterior pane had a maximum temperature of around 340 degrees Celsius, and these temperatures allowed enough thermal equilibrium where the pieces of glass never broke. The team would like to express our gratitude towards our professor, Dr. Kimmel, and our sponsor, Dr. Szymanski. Thank you.